Okay, and the last example, this is sort of a real-world example using data from a rocket launch in 1992, actually. I'm not writing all of it down because, of course, you've got that and it's way too much to write. But our velocity function, which has been modeled from the data, is given here, but we're asked to find the absolute maximum and minimum values for acceleration in a 125-second period. So the function we want is acceleration, and the acceleration, which I'm going to call A of t, is the rate of change of velocity. So that means, using our interpretation of the derivative, that is the derivative of the velocity function. So our acceleration function, we're going to take the derivative here, so we're going to multiply 0.0015 by 3, and that's going to be 0.0045 x squared. And then we're going to subtract, we're going to multiply 1155 times 2, so we're going to get 0.231 x, and then plus 24.9817. So here is our function, and then the interval is 0 to 125. Okay? So now, according to our method, first thing we're going to do is we are going to check the values of the function at the endpoint. So that's a of 0, that's one of our endpoints. So we're going to get 24.9817. And then for a of 125, we're going to put 125 in for our x values, and this is going to get us, which I've already calculated here, 66.4192. So those are the endpoints. The next thing we need is the derivative of our acceleration function, which incidentally is called jerk, because if you have a sudden change in acceleration, you get a jerk. All right, so now we're going to take the derivative here. When we take the derivative of 0.0045 x squared, we're going to multiply the 0.0045 by 2, so we're going to get 0.009 x. The derivative of the 0.231x term will give us 0.231, and then the derivative of the 24.9817 will be 0. So this is what we have, nice simple function to work with. It's a polynomial, so we don't have to worry about the derivative not existing. So to find our critical numbers, which is the next thing we need, we're going to set this equal to 0. And then we just have to solve for x. So we're going to get 0.009 x, and this is the wrong place to put that. So I'll do that on the next line here. We're going to get 0.009 x is equal to 0.231. So x is equal to 0.231 over 0.009, and that is approximately 25.667. Okay, so I need to erase. I'm going to save some of our values up here. A of 0 is 24.9817. A of 125 is 66.4192. And now I'm going to erase a little bit in here, because what we need to do is figure out, with our critical value, the value of the function, and that's the last bit we need to do. So that's our 25.667. So we're going to look at A of 25.667, and that is going to give us, again, I've already worked this out, plugged in 25.667 in for x here and here, and this gives us 22.0172. And now what we need to do, we're looking for the absolute maximum and absolute minimum accelerations on our interval. So we're going to compare A of 0, A of 125, and A of 25.667. And we see, after looking at those values, the absolute maximum acceleration is the 66.4192. And then our units for this are in meters per second squared. And we know this because our units for velocity were meters per second, and the units of the derivative are the units of the function, that was meters per second, divided by the units of the input. So the units of the input are seconds. So we get meters per seconds divided by seconds, and that gives us our meters per second squared. And then the absolute minimum acceleration in this 125-second window, which is about 2 minutes, that is our 22.0172 meters per second squared. And just to give us a little bit of context, so I don't really know how much experience any of us have with this, but another sort of unit, when we talk about G force, that's the force of gravity. So the 66.4192, just for reference, this is about 6.8 Gs. And this minimum acceleration here, the 22.0172, is about 2.3 Gs.